So today we're working on the 2017 BC Calculus free response questions, and these are the video solutions. As always, I'd encourage you to pause this video here real quick and really figure out what the question is asking for before watching these solutions. So I'm just going to highlight all the important pieces of the question, and basically what's going on here is that we have a tank and it is 10 feet, but the question gives us the cross section. This table right here gives us the cross section of the cross section area, the area of the horizontal cross section of the tank at every height. Well, not every height, but at the height 0, 2, 5, and 10 feet. So we need to highlight the important things here. The height is 10 feet. What else do we know? We know that the function a is continuous and decreases as h increases. Those are really important pieces. And so moving on, A asks us to use the left-hand Riemann sum with 3 subintervals indicated by the data in the table to approximate the volume of the tank. And don't forget the units. So a left-hand Riemann sum is basically a poor man's way of finding the integral. So we're basically being asked to find the integral of a of h dh, the integral of a of h dh of, I'm using the table that we have above, but it's the left-hand Riemann sum. And so we're just going to do what we know how to do and take the first value, which is this, multiply it by the change in h, take the second value, which is this, and multiply it by the change in h, and do the same thing for the third value. And so you should get what's going on with the Riemann sums. So basically we have the change in h, which is 2 minus 0, multiplied by 50.3, plus the change in h, which is 5 minus 2, multiplied by 14.4, plus the change in h, which is 10 minus 5, multiplied by 6.5. And these are our 3 subintervals. And if you just, this is the calculator section, so you can really just plug this into your calculator, and you should get 176.3. Now for the units, we're multiplying the height, the change in height, by the cross-sectional area. We're finding the integral of that. So that's just the volume. So our volume is cubic feet, or feet cubed. So we have successfully answered A. Now B asks us whether the approximation is an overestimate or an underestimate. Now I highlighted that the function is continuous and decreases as h increases. So to jog our memory, let us do an example of a decreasing function. And let's not forget, a decreasing function that is continuous doesn't have to be a straight line. It could be any weird looking function that's just decreasing. It's decreasing from the integral from the interval of here to here. Let's label these points A and this point B. Now with this function, actually this would be a bad example. It would be more appropriate to do something where everything is positive, so it's more similar to our example over there. So just any function that's decreasing, really. So let's say from A to B. And what we're doing with the left-hand Riemann sum is we're trying to approximate the area under this line using rectangles that look like this, right? We're using rectangles that look like this. So we're just summing up the area of all these rectangles to find the area under this. And so the function is decreasing, and with a left-hand Riemann sum, the left-hand rectangles like this, at every point we're taking the left part. We're using this to approximate. We're using this. And what you would find is that this is actually an underestimate, because at every point the area is actually is an overestimate, I should say, and not an underestimate, an overestimate, because at every point the area is higher than what it actually is. because the function is decreasing. So the area is always higher than what it actually is. And we can see that from this graph right here. So all we have to say is that the area is decreasing, is that the function is continuous and decreasing, so it is an overestimate. The function is continuous and decreasing, therefore with a left Riemann sum it is an overestimate. That's all we have to say. And now C. This asks us to find the area in square feet of the horizontal cross-section, and it gives us what the function is actually modeled by. So this is what we were trying to find before, but using a more rough approach, a more layman's method. Now we actually have the function, and so to find the volume of the tank, we just need to do the integral of f of h dh. So again, simply we'd be taking, the volume is simply, because it's 10 feet tall, it's the integral from 0 to 10 of f of h dh. That's what the volume is. And so this is simply the integral from 0 to 10 of, we have the function given, 50.3 over e to the 0.2 h plus h. 50.3 over e to the 0.2 h plus h dh. And again, we're very thankful because this is the calculator section, and if we plug this in correctly, we should get 120.6. 120.614 feet cubed. Cubic feet. That's what the answer is. And this is a perfect example of what you should not do, because the correct answer is actually 101.325 cubic feet. I'm sorry, I just had to double check that. I plugged in e to the 0.2 x plus x in the, it was in the power of x plus x. That's a very very simple mistake that probably tripped up a lot of people. So moving on, D asks us now to find the rate at which the volume of water is changing with respect to time when the height of the water is 5. But it also tells us the rate at which the height is changing with respect to time when the height is 5. So what do we do? First of all, let's write down what we're trying to find. We are trying to find dv dt. So at this point, at t equals 5, by the way, we're trying to find dv dt at t equals 5. And this equals dash for now. We don't know what it is. But what the question gives us is dh dt. It gives us the rate at which the height is changing with respect to time at t equals 5. And that is equal to 0.26. That is equal to 0.26. So what we need to do now is find a relationship between v and dh dt. So we already have v. We found that in C. But to find dv dt, we just need to break it down. dv dt equals dv dh times dh dt. We know this because if we actually do these would cancel. Dh would cancel dh. But we are using this property to find dv dt. So we know dh dt, but do we know dv dh? dv dh is just the derivative of v with respect to h. So dv dh is equal to ddh of the integral from 0 to 10, ddh of the integral from 0 to 10 of f of h, the function f of h dh. Now, because of the first fundamental theorem of calculus, and it's not at, this should be just without the limits of integration. Because of the fundamental theorem of calculus, we know that this is just exactly the same thing as big F of 5. We know that that is what this is. So dv dh at h equals 5 well, this is f of h, but because we're trying to find it at f at t at the height equals 5. So dv dh is just equal to big F of 5. And that is equal to just plugging in 5 into this function that we already have here, plugging in 5 into this function. And it's the function without the integral. So let's pull it up from here. That is just plugging in 5 as h into this right here. So it's 50.3 over e to the 0.2h plus h. So f of 5, which is 50.3 over e to the 0.2 times 5 plus 5. That is f of 5. Now we have found dv dh at h equals 5. This is at h equals 5. And now I'm just noticing that I wrote t equals 5. This should be h equals 5. At h equals 5. This is at h equals 5. And so we have found that at h equals 5. And to find dv dt, that's just equal to dv dh, which we have right above, which is just exactly this, times the h dt. But what is the h dt? The h dt is simply 0.26. 0.26. And that, if you just plug that into the calculator, we have to plug this into the calculator and multiply it by 0.26, we should get, if we do it correctly, 1.694. And the units are feet cubed per minute. And so we have successfully answered D. But just because I stuttered a little, I know it must have gotten a little confusing. So I'd go over D one more time. We have dv, dh dt, it is given to us, and we also have v. But the question is asking for us to find the rate at which the volume of water is changing with respect to time when the height is 5. So we are trying to find dv dt at h equals 5. And dv dt we got to be dv dh times the h dt. So when we found dv dh by taking the derivative of v with respect to h, we got that that's just equal to f of h. That's what this is right here. And we're finding this at h equals 5. So that is equal to just plugging in 5 into the function a that we already had initially. So dv dt equals dv dh times the h dt, which is 0.26. And that's how we get our final answer. We have successfully answered the full question.